9.9 Lesson 2, Representation of Functions by Power Series. Our objectives for today are: 1. You'll be able to write the partial fraction decomposition of a rational function and then represent the rational function using geometric power series. As a part of that process, towards the end of it, you'll be able to use operations with power series to aid in representing functions with geometric power series. So these two go together. The third one is separate. Find a power series representation for a function by differentiating or integrating the power series for another function. So you can think of these as two separate lessons that we're doing together in one day. So vocabulary, partial fraction decomposition, and operations with power series. So let's look at objectives 1 and 2 now. What we'd like to do with number 14 is represent this function with a power series. And the way we're going to accomplish that is by first rewriting the function using partial fraction decomposition. So to do that, you need to begin by factoring the denominator, which factors as 2x minus 1 times x plus 2. Once you know that, you can write what we call the form of the partial fraction decomposition for this rational expression. What you will have are two partial fractions. The denominator of the first one will be 2x minus 1. The denominator of the second one will be x plus 2. And the numerators are constants that we need to solve for. Before we go on any further, this is what I stated at the beginning, but I wanted to write the instructions for this problem in words. This is what we're trying to accomplish. We're trying to find a power series for this function centered at 0 that represents the function and determine the interval of convergence. In other words, for what values of x can we represent this function with the power series that we will find for it. And as we have already begun doing, we write the function, or we rewrite the function using partial fraction decomposition. Of course, we still need to find the values for the constants a and b. And what each of these partial fractions will be are functions that can be represented by geometric power series. So we may use what we learned yesterday to represent each of these partial fractions with a geometric power series and find the interval of convergence for each of those geometric power series that will represent the two functions that we will have for the partial fractions. So that's where we're going with this problem. We want to represent each of these partial fractions with a geometric power series, find the interval of convergence for each geometric power series, and then we will learn about operations involving power series. We'll be able to add the two power series together and find the interval of convergence for the sum of the two geometric power series. So how do you find the partial fraction decomposition for the function? We begin by factoring the denominator, and for each factor in the denominator, we write this, which we call the form of the partial fraction decomposition. Why does it have this particular form? Because our denominator factors as a product of two distinct linear factors. Now, if the denominator had factored differently, we would have a different form of the partial fraction decomposition. But we're restricting our consideration to this particular form of the partial fraction decomposition, which will result when the denominator factors as a product of two distinct linear factors. So that being done, the next step in the process is to solve for the constants a and b, which are in the numerators of the partial fractions. So the next step to accomplish that is to multiply both sides of this equation by the LCD. So when you multiply by 2x minus 1 times x plus 2 on the left side of the equation, you will just be left with 4x minus 7. And when you multiply by 2x minus 1 times x plus 2 on the right side of the equation, you will distribute the LCD to each partial fraction. And when you do that, the denominator of each partial fraction will cancel with one of the factors from the LCD, and that results in a times x plus 2 plus b times 2x minus 1. So this is called the basic equation. And how do you solve the basic equation? You assume, because what are we trying to do? We're trying to find the values of the constants a and b that would make this equation here an identity. In other words, we want to represent our rational expression in an equivalent form so that the two sides would be equal for any value of x. So our objective is to figure out what the constants a and b need to be so that this equation here will be an identity. So we work backwards. We assume that we have an identity and work backwards to find the values of the constants a and b. So if we assume that this basic equation is an identity, it would be true for any value of x. And we're going to choose values of x that make it easy for us to solve for the constants a or b. So if we choose x to be negative 2, this term here will become 0. And if that term is 0, I can simply solve for b. So if I substitute negative 2 for x here, I will have 4 times negative 2 minus 7, which is negative 15. And of course, this term will be 0, and this term will be 2 times negative 2 is negative 4, minus 1 is negative 5. So I'll have negative 5b on the right side is equal to negative 15 on the left side of the equation. Dividing both sides of the equation by negative 5 gives me that b is equal to 3. So now, what do I need to choose x to be so that I can easily solve for a? I need to choose x in such a way so that this term from the basic equation will become 0. So if I choose x to be 1/2, 2 times 1/2 is 1, and 1 minus 1 is 0. So I should choose x to be 1/2 so that this term from the basic equation will become 0, allowing me to solve for a. So if I choose x to be 1/2, then on the left side of the equation, 4 times 1/2 is 2, 2 minus 7 is negative 5, and on the right side of the equation, 1/2 plus 2 is 2.5, or 5/2, so I have 5/2 a. So what is a? Multiply both sides of the equation by 2/5, and you get that a is equal to negative 2. So now that you know the values of the constants a and b, we're able to rewrite number 14, the function given at the beginning of number 14, as a sum of two partial fractions. So we are able to rewrite number 14 as you see at the very bottom of my screen. Basically, we're able to rewrite it as a sum of two functions, each of which resembles the form a over 1 minus r. And the significance of being able to write our function that we began with for number 14 in this form is that each of these partial fractions, as I just stated, is in the form a over 1 minus r. Not exactly in the form a over 1 minus r, but it could be manipulated to be in the form a over 1 minus r. Each of these can be manipulated algebraically to be in the form a over 1 minus r, so that like we did yesterday, we may represent each of these two partial fractions with a geometric power series centered at 0. And of course, since the sum of these two fractions is representing the original function for number 14, we can add the two geometric power series to get a power series that would represent the function for number 14. So that's where we're going with this example. So what we need to do is the following. As we've already stated, number 14 can be written as a sum of two partial fractions, and for each one, you're going to represent each partial fraction with the geometric power series. So we're looking at properties or operations with power series. If you have two power series, what can you do with two power series? One of the operations you can do is you can add the two power series together. And the way you do that is simply you isolate x to the n in the nth term of each power series, and then you would factor out x to the and then you would add the nth term. You would add, and then you would add the nth terms of the two power series and factor out the x to the n. So for example, look at just what we have here. So we have operations with power series. Let f of x be the power series with nth term a sub n times x to the n, and let g of x be the power series with the nth term b sub n times x to the n. So what are we going to do to combine these two power series to get f of x plus g of x? We simply do this. We're going to add the nth terms of the two power series together. But what you want to do is you want to look at the two nth terms and you want to factor out x to the n from that sum. And when you do that, you will get a sub n plus b sub n times x to the n. So at the end of the process that we will look at for number 14, we will be using property number 3 from operations with power series. You could also apply this property if you had a subtraction. You would just be doing subtraction instead of addition. So while we're here, we'll take a look at the other two properties or the other two operations with power series. So you're given these two power series, and we looked at 3 already. Number 2 simply says you have this power series for the function f to begin with, and if you want to find the power series for f of x to the n, all you do is, in place of x in the power series for f, replace x with x to the n. And that would give you f of x to the n is equal to the power series for f evaluated at x to the uppercase n. So you will have this. And of course here you have a power of a power, so when you multiply the exponents, this is what you will have. And let's take a look at number 1. What is number 1 stating? Number 1 is stating that if you have the power series for f evaluated at some constant times x, again, what do? You're just going to replace x in the power series for f with k times x. So you will have f of k times x is equal to the power series for f evaluated at k times x. So you'll have k times x to the nth power, and that would simply be k to the n times x to the n. So that's what you have for property 1. And these properties can be used for some of the problems from the homework tonight. So again, why did we look at those operations with power series? Because this is what we want to do to complete our problem for number 14. And it's been a couple of minutes since we looked at the beginning of the problem, so just to remind you, what are we trying to accomplish? For number 14, we have this function g of x, 4x minus 7 divided by 2x squared plus 3x minus 2. And we want to find a power series for this function centered at 0 and determine the interval of convergence. And how are we going to do it? By rewriting g of x using partial fraction decomposition, so that we will have two partial fractions, each of which can be algebraically manipulated to fit the form a over 1 minus r, so that we may represent each one by a geometric power series and find its interval of convergence. And once we have two geometric power series for these two partial fractions, we will use this property for operations with power series to add the two power series together. So now we'll go ahead and find a geometric power series for each of these two partial fractions. So now we will take a look at the first partial fraction. Again, we need to algebraically manipulate it so that it will be in this form. And let's see how we can accomplish that. And once it is in this form, we may represent it with a geometric power series and find its interval of convergence. So first of all, our center is 0, so it's a little bit easier for that reason. So you just need to go ahead and get this function in the form a over 1 minus r. So you can see that the 2x, the term that has x, we want that to be the common ratio, so that we will have a geometric power series. So the first thing that you do is rewrite the denominator so that you have negative 1 plus 2x. But we need to have positive 1 because we need to have a over positive 1 minus r. So we can accomplish that just by taking what we have for the function and multiplying by negative 1 over negative 1, which is, of course, just 1. So when you multiply the numerator by negative 1, you get positive 2. And when you multiply the denominator by negative 1, you get 1 minus 2x. So that now we have something that resembles the form a, which would be 2, over 1 minus r, which would be 2x. So a is 2 and r is 2x. So now we're able to write the geometric power series for the first partial fraction, and it would be the infinite sum from n is equal to 0 to infinity of a, which is 2, times r to the n. R is 2x, so we have 2x to the n. And we know by the convergence of a geometric series theorem that a geometric series will converge when the absolute value of its common ratio is less than 1. So the absolute value of the common ratio would be the absolute value of 2x, and we need for that to be less than 1 so that our geometric power series will converge. So you write this absolute value inequality as a compound inequality, and you will divide each part of the compound inequality by 2, and you get the interval of convergence is from negative 1/2 to positive 1/2, excluding the endpoints. So what have we done? We have found a geometric power series centered at 0 for this partial fraction, and we have also found that this geometric power series will exactly represent the function negative 2 over 2x minus 1 on this interval of convergence. We need to do the same now for the other partial fraction. So here's the other partial fraction, and it is almost in the form a over 1 minus r. But again, we want to make sure that the term that has x is going to be a part of the common ratio. So we write 3 over 2 plus x. Now, the only issue is I need to have 1 minus r in the denominator. Right now I have 2 plus x. So how do we deal with that? Well, first of all, you can make sure that you have a 1 here. But you don't have a 1, you have a 2. So you're going to multiply 3 over 2 plus x by a form of 1. You're going to multiply it by 1/2 over 1/2, which is, of course, a form of 1. So when you do that in the numerator, you'll have 3 times 1/2, which is 3/2. And in the denominator, you will distribute the 1/2 to the 2, and that gives you the 1 that you want. Distribute the 1/2 to the x, and you get x over 2. But you still have 1 plus x over 2, and of course you need 1 minus. So that's easy to do, because you can write 1 plus x over 2 as 1 minus negative x over 2, because when you subtract a negative number, it's the same as adding. So now we have our function algebraically manipulated so that it is exactly in the form a over 1 minus r, so that we may write a in the numerator, which would be 3 over 2, over 1 minus r. 1 minus r would be negative x over 2. So now that it's in this form, we're able to represent our function with this geometric power series. The infinite sum from 0 to infinity of a, which is 3 over 2, times r, negative x over 2 to the n power. So what is the interval of convergence for this geometric power series? You need to look at the absolute value of the common ratio and set that less than 1. So rewrite the absolute value as a compound inequality, multiply all 3 parts of the compound inequality by 2, and our interval of convergence is from -2 to +2. Now it's time to put our work together. This is the function that we began with. We know it can be written as a sum of these 2 partial fractions. And for each partial fraction, we were able to represent each partial fraction with a geometric power series. So the first partial fraction may be represented with the geometric power series that I'm writing here, that we found earlier. And we know that its interval of convergence is from -1/2 to +1/2. And the second partial fraction may be represented with this geometric power series that we just found. And its interval of convergence is from -2 to +2. So what are we going to do to complete the problem? Because the function g of x is the sum of these 2 partial fractions, we need to add the 2 geometric power series we have for each of the 2 partial fractions. And when we add 2 geometric power series, or any 2 series, what will be the interval of convergence for the sum of the 2 series? It will be the intersection of the 2 intervals of convergence. In other words, the smaller set of x values. Basically, here's how you should understand it. When you add the 2 power series together, the interval for the sum of the 2 power series will be the set of x values for which both series will converge, And that is why you've got to make sure that you've got the x values for which both power series will converge, and that happens at what we call the intersection of these 2 intervals. So let's go ahead and take a look at what we mean by that. The easiest way to understand that is to draw a number line. So here we have a number line. Here we have 0. And let's say this is -1, and this is +1. This is -2, and this is +2. And from negative 1/2 to positive 1/2, that would be over here. And from negative 2 to positive 2, that would be over here. So what is the interval where we have the intersection of these two intervals? That would be over here. So the interval of convergence for the sum of our two-power series is the intersection of these two intervals, or from negative 1/2 to positive 1/2. We've established that, but now we still have to go ahead and add these two power series together. So how do we do that? Let's take a look. And then that would complete our example for number 14, because after we add the two power series together, we would have a power series, not necessarily geometric anymore. These are geometric, but when we add them together, let's see what we get. But we will have a power series that represent the function g, and it will be centered at 0. And how do you do that? You've got to work with the nth term of each power series, and you can begin by isolating x to the n in the nth term of each power series. And here's how we do that. So we're going to do it like this. So you just use properties of exponents. So now you're going to have 2 times 2 to the n times x to the n. Because you can distribute this exponent n to the 2 and to the x. And then you have plus, from n is equal to 0 to infinity, 3 over 2. And you can look at what we have here. You have negative 1, you have x, and you have 2 in the denominator. So you can write that as negative 1 to the n times x to the n over 2 to the n. Again, just distributing the exponent n to each part that we have of the quantity that is being raised to n. So now that you have that, what have we accomplished? Well, let's see. We have from n is equal to 0 to infinity. You can simplify 2 times 2 to the n as 2 to the n plus 1 power, and you have x to the n plus, and then here we have in the denominator you have 2 to the first times 2 to the n. That's going to be 2 to the n plus 1. So we have 3 over 2 to the n plus 1. And you also have negative 1 to the n. So you can write that over here, negative 1 to the n. And then you have the 3. And then you have 2 to the n plus 1 power in the denominator. And you have x to the n. So what are you going to do now? I'm going to erase some work here so that I have room to continue. So I'm going to take my work from what we have here at the bottom and bring it to this level. And all we're going to do is we're going to add the two power series together. And when we do that, we're going to have 2 to the n plus 1 times x to the n plus negative 1 to the n over times 3 over 2 to the n plus 1 times x to the n. And how do you complete this problem? Again, all you do is the following. You're just going to factor out x squared from each of the two terms. And when you do that, you would get 2 to the n plus 1 plus negative 1 to the n times 3 over 2 to the n plus 1 times x to the n. So we have a power series. Now, is this a geometric power series? Is it in the form a times r to the n? Not quite. We don't really see that because we've got n in different places. So it's probably not a geometric power series because I don't think we can write it in the form a times r to the n. It is a sum of two geometric power series, but what we have is a power series, and it represents the function for number 14. On the interval of convergence, which is the intersection of the intervals of convergence for the two geometric power series for the two partial fractions. So the interval of convergence would be from -1/2 to +1/2. So what we've done are objectives 1 and 2. We looked at how to write the partial fraction decomposition of a rational function and then represent the rational function using geometric power series. And we used operations with power series to add the two geometric power series to get the power series that represents our problem that we began with, and we found the interval of convergence for that. The next objective, since we've already gone a long time today, and we've done about 30 minutes, we're going to leave that for another lesson, which we will do tomorrow. And it will be a separate lesson, and it will be finding a power series representation for a function by differentiating or integrating the power series for another function. So we'll look at that tomorrow.